Professor Arkady Leiderman is a specialist working in pure topological spaces, in the function analysis, applications of topology in analysis and topological groups. And this is our program for these lectures. We just selected people from this area of mathematics. And he will give today a talk under the title Delta Spaces X and Distinguished Spaces CPX.
Okay, thank you, Jerzy. Thank you for invitation. Thank for everybody who came to the lecture, because the lecture is rather specific in some area of research which we are doing together with Jerzy last years. And you see in the title three notions: delta spaces, distinguished, and CPX. So I should start with the explanation what all those notions mean. But first of all, let me tell you again that this is a joint research which we did together with Jerzy last year. We have 3 published papers in good journals, and also I have the first paper with Vladimir Tkachuk, another paper with Paul Sheptitsky. According to the names, you can guess that Tkachuk is Ukrainian, but he is not. He's from Mexico, 30 years old. Yes, already in Mexico. And Paul Sheptitsky is Polish, but he's Canadian. He was born in Canada, right? Okay. Now, I start with the definitions of very special subsets of the real line R. Believe me that these definitions are rather classic today. But first of all, what is a Q set? A subset X of a real line is called a Q set if each subset of X is O F sigma equivalent is G delta. F sigma means a countable union of closed subsets, and G delta means dual notion. It is a countable intersection of open set. So it looks like some exotic set, but it was invented by Felix Hausdorff, and as far as I understand, he gave a name Q set because this is like the set of rationals Q. Okay, so if you take, for example, any countable set like rationals, then this property that each subset is F sigma is, of course, fulfilled. The second definition, lambda set. Lambda set, it is a weaker property. It says that only countable subsets of X are G delta. And the most important for us is the notion of a delta set. Okay, the definition of a delta set looks like a long one and less understandable. I just read it. The idea is the following: that if you have a decreasing sequence of subsets, no assumptions about sets D, we only require that the intersection of this decreasing sequence is empty, then you can enlarge these sets. You can somehow find bigger sets, Vn, which are open, and still the intersection of all those sets Vn is empty. This is a definition of delta sets, and now I tell you what is the relation, what between all those notions, what is the status of existence of these sets. Okay, so this is a long story, but to do it shortly, Q set is stronger than delta. Q set implies delta. Lambda exists even in the FC. This is a result, by the way, of Kazimierz-Kuratowski. And now, what do we know about the existence in the FC? I mean, Zermelo-Fraenkel axiom system. What do we know about the existence of uncountable Q set? The story is the following. From one point, if you assume continuum hypothesis, then there are no uncountable Q sets. Why? Because this is a theorem of Hausdorff. And actually, this result was extended also by some prominent mathematicians like Václav Sierpiński and Fritz Rothberger. Okay, so many famous mathematicians, they were involved in this business. On the other hand, if you assume some more specific axioms, which is called Martin axioms plus negation of continuum hypothesis, then we know that if you take any subset with a cardinality less than continuum, then it must be a Q set. Okay, so two extremes. If you assume CH no uncountable Q sets, but if you assume Martin axiom plus negation of CH, then you have plenty of uncountable Q sets. What is the situation about delta sets? It's pretty much similar. The situation is that again, if you assume continuum hypothesis, then you do not have actually uncountable delta sets. This is the result of another mathematician, Theodor Przemyślski. I'm not sure he was in Poland. He was in the United States, maybe. And still, there is some very difficult, very technical work by Robin Knight, and he proved that consistently, it means in some very special designed model theory, model of set theory, you have a delta set which is not a Q set. So these notions, delta and Q in theory, are different. Okay. So the question is, what is the use of these notions for general topology? I give you just one example how specialists in general topology use these exotic sets. Okay, there exists maybe a very famous problem. It is so-called normal Moore space conjecture. I do not give you the whole definitions because it's not the main topic of my talk. But anyway, many topologists, they were trying to prove that every normal Moore space is metrizable. And the motivation was that all known Moore spaces that you can construct by hand, they are not metrizable because they are not normal. And I give you a very well-known example of particular such space, which is called Nemitsky plane. Maybe you even remember from your basic course in general topology, what is it? Nemitsky plane. Do you remember? Usually it's a part of a course in topology. Second year. Okay, I remind you what it is. Okay, as a set, Nemitsky plane is just half plane, okay, closed half plane, let's say upper half plane, and you define the topology on this half plane the following way. So if you take a point which is above the x-axis, if you take the point from, in my notation, the point from L2, which is above the x-axis, then the basic open sets are usually Euclidean balls. Okay, you do not change topology in those points, but in points which belong to the x-axis, the basic open set looks like a tangent ball plus this point itself. This particular space is called Nemitsky plane, and what is famous for? It is famous that this is the first example of the space which is Tikhonov but not normal. This space is not normal. Now, what was the idea? American mathematician Jones, he suggested instead of the whole x-axis to take just a subspace, some set x. Okay, so we consider the subspace M of X, which is a subset of the whole Neminsky plane, but instead of the whole axis, we take just a subset X. And then there are two results. You see them on the blackboard, on the screen, that this particular space M of X is normal if and only if this characterization, your set X is a Q set. And another observation by another mathematician that this M of X is countably paracompact if and only if X is a delta set. This is the most striking example of using of Q sets and delta sets in topology. There are many. I gave you only one. Okay, now another, not visible, but the title is what is this distinguished locally convex space. So this is another story. I ended with the background from the set theory. Now I'm talking about locally convex spaces. So there is some exact definitions. The definitions are due to Dieudonné and Schwartz. And the definition says that a locally convex space E is called distinguished if every bounded subset of the B-dual of E in the weak-stack topology is contained in the closure of the weak-stack topology of some bounded set of E. It is official definition. There are some other equivalent definitions, like E is distinguished if and only if the strong dual is barreled. Okay. Now I need to find some motivation for these objects, and we can find some words of motivation in papers by classics of this stuff, in the papers by Dieudonné, etc. And Dieudonné himself wrote that classifying topological vector spaces according to their behavior with regard to the validity of the main theorems of function analysis. So they invented in 50s many other notions related to locally convex spaces because they wanted to know what is the frontiers for those main classical properties of Banach space theory. Okay, now my motivation is somehow to combine two lines of research. One notion comes from set theory, it is delta sets. Another notion comes from function analysis, this is distinguished locally convex spaces. And we found a very good relation between them when we consider a very special locally convex space. I will say later what is it. But what is our, let me say, new notion? Instead of delta sets of real line, okay, now we remove the assumptions that we are dealing with subsets of real line. We just define a Tikhonov space X without any a priori assumptions. We say that the Tikhonov space X is called delta space if the same definition of delta set still holds. Okay, again, what do we have? We have that if for every decreasing sequence of subsets of X without any assumption, any decreasing sequence of subsets with empty intersection, you can find another decreasing sequence of open subsets such that each Dn is contained in the open set Vn for every n, and the intersection of this bigger family still is empty. This is an official definition of a delta space. No metrizability, no subset of real line. And now the main object of our research is a very special space which is called CPX, the locally convex space CPX. What is it? This is a function space. This function space C of X of all real valued continuous functions, but it's not North space. It is a locally connect space, the so-called pointwise convergence topology. Okay, so CPX is the object of our research. It means that CPX is considered just a subspace of the product R to the Rx. And in general, what are the questions which we ask in this area? We ask, how are the properties of X and CPX related to each other? What are the dualities? So how to characterize property of CPX in terms of the properties of X? This is a general question. And what I can remark? I can remark that, of course, the roles of X and CPX are not equivalent because CPX carries a lot of extra structures. CPX can be viewed as a group, topological group, or a ring, or linear space, while X is just a topological space. And in my talk, for our purposes, we regard CPX like a locally convex space. Okay, for us, CPX is a very important example of locally convex spaces. And this topology of pointwise convergence topology is the weakest topology among all other natural topologies which you can put on the space C of X. Now, what is one of the most striking theorems which shows the difference between the properties of pointwise topology in comparison with norm topology? Okay, here you see such a result in the bottom. It is known that if you consider two spaces, Cp of X and Cp of Y, and assume that these two linear spaces are linearly isomorphic, then topological dimensions of X and Y are equal. Dimension of X is equal to dimension of Y. This result does not exist for Banach space. For Banach space, the situation is different. If you take, instead of X, like just a segment, and instead of Y, you take a square, then it's known, it is Milutin theorem, that Banach space of function of one variable is isomorphic to the Banach space of the functions of two variables. For pointwise topology, is not so. Okay, now I start with our result. So this is a result from our joint paper with Ferrando, with Jerzy and Saxon. It says that these four items are equivalent. What is equivalent? CPX is distinguished, this is the first one. Then we have some characterization of this property in terms of how this CPX lies inside a bigger space, inside the product R to X. And it says that CPX is a large subspace. What does it mean CPX is large? It means that for every bounded set A from a bigger space, there is this bounded set B in CPX itself, such that A belongs to the closure of B, this biggest space R to X. And the third item says that it is true if you take just one function from R to X. And the first characterization, completely in the language of locally convex space, it says that strong dual of CPX carries the finest locally convex topology. This is a very nice and good theorem, but you see one disadvantage of this language. What is bad? The bad that the definition, the characterization is in the extra notions, not in the language of internal properties of X. So the natural question, how to find a characterization of CPX being distinguished in the language of internal properties of X. This theorem doesn't give such a description, And this was exactly our motivation to get the following important result. This theorem we obtained together with Jerzy, and it says that these three properties are equivalent. First, CPX is distinguished. The second one says that any countable disjoint collection of subset of X admits so-called point finite open expansion in X. And the third one, this is our result. X is a delta space. So the bottom line, CPX is distinguished if and only if X is a delta space. This is the internal description of CPX being distinguished. And then, with the help of this theorem, we managed to find many other results. Okay, so first, examples of delta space and spaces which are not delta space. How to construct them? It's not so obvious at all. How do we construct one example of a delta space? And also, it's not so trivial how to construct an example of the space which is not delta. So there is a nice notion, a nice sufficient condition which allows us to show that certain spaces are delta space. This definition you see on the screen, it is 4.1, and the definition is the following. We say that a family, this calligraphic Nx of subsets of a Tikhonov space X is called a point finite neighborhood assignment if what? For every point, we fix one open neighborhood, and this cover is point finite. This is a definition, okay, for each point to fix a neighborhood, and this cover should be point finite. And then we have a simple example. Simple example says that every countable space X admits such a point finite neighborhood assignment. What is an assignment? You do it by induction. You take an enumeration of all points from X, and then you define it as follows. If the point is number xn, then the open neighborhood of this point xn is just X minus all points with indexes which are less than n. And then this set will be open because what? You remove only finite sets. So you remove finite set, you get open. And this is indeed a point finite assignment. The theorem says that once you have a point finite neighborhood assignment, then CPX is distinguished. So in our language, it means that once you have a point finite neighborhood assignment of the space, then your space is delta. Okay, this is a short proof of this result. Once you have any collection of pairwise disjoint subsets, then you define U gamma as just the union of those elements from assignment, and then it will be a point finite open expansion of your family of pairwise disjoint subsets, and according to our description, it is equivalent to B delta. Now, what are other examples of the spaces which admits point finite neighborhood assignment? Now, I already told you that any countable set admits such assignment. Another easy example is any space X which has only finitely many non-isolated points. Now, in general topology, this object is maybe simple, but still, if you wanted to show that CPX is distinguished for such a simple space, it's not so trivial task. But anyway, our proof goes as follows. We just define a point finite neighborhood assignment. What is an assignment? If point is isolated, we take it itself, and otherwise, for those finitely many exceptional points, we declare that the neighborhood is just the whole X. And then this is a point finite assignment, and then we have a theorem that type X is distinguished. And another more complicated example is about so-called Eberlein compacts. What is Eberlein compact? Eberlein compact is a weakly compact subset of Banach space. So if you take any Banach space, equip it with weak topology, any compact subset of such Banach space with weak topology is called Eberlein. And another notion from general topology, also known as X is called scatters. If every subset of X has in A isolated point. So the result says the compact space X admits a point finite neighborhood assignment if and only if X is exactly scattered Eberlein compact space. And in particular, if you have a scattered Eberlein compact space, then CPX is distinguished. Okay, so this is a nice class of compact spaces such that you know that CPX is distinguished. All Eberlein compact. Okay, let me say you a few words about the class of delta spaces. Okay, I promised you to give also some examples which are not delta spaces. And here with Paul, we obtain several simple classes of topological spaces for which we know that they are not in delta. For example, if you take any hereditarily separable space with a cardinality continuum, then this X is not delta. If you take any separable and hereditarily linear space, again, if the cardinality is continuum, then it's not in delta. As a corollary, you have the following propositions. And if you take so-called Sorgenfrey line, and if you take any subset of this Sorgenfrey line with cardinality continuum, then such X cannot be delta. So you have many examples of spaces which are not delta. The question is, what can we say about the separable metrizable delta spaces? So again, we used to, in Banach space theory, for example, to have only metrizable spaces, okay? So the existence of uncountable separable metrizable spaces X is such that CPX is distinguished. You cannot decide is by tools of the FC, so it is independent. It is equivalent to some other extra axioms of set theory. And in particular, we can say that there exists an uncountable separable metrizable space X such that CPX is distinguished if and only if you have a solution for more problems. So if and only if you have a separable, countably paracompact and non-normal morph spaces. So our research is mostly about non-metrizable spaces. For metrizable spaces, you depend on extra axioms. Okay, the section 5 is about compact spaces. The most interesting and the most important part of our research is about compact delta spaces. Okay, and here we have several interesting results. Okay, what is the structure of a compact delta space? What can we say about the structure of compact delta spaces? So the first result is the following, that every compact delta space must be scattered. This was our first result. Then we managed to generalize it to even for countably compact. So any countably compact delta space is scattered. Another result says that every check complete delta space must be scattered. Now, if you know a topological space is called check complete, if it is G delta, you need stone check compactification. And in particular, if you assume that X is the first countable compact space, I mean the compact space with first axiom of countability, then X can be delta if and only if X is just countable space. Okay, another observation that if you have any non-scattered space, then stone check compactification of beta X of this space cannot be delta. And this corollary, which sounds like some innocent corollary, has some nice applications. Okay, now what is the main question? We wanted to know maybe scattered compact spaces and delta compact spaces are the same classes. Okay, we proved first that every compact delta is scattered, maybe it's the same, and it turns out that it's not the same class. Let us consider the space of ordinals. Okay, what is the space of ordinals? We take all countable ordinals from 0 to omega 1. We consider this topological space as a linear ordered topological space. And if you wish, you can add also the last point omega 1 itself, and then it will be a compactification. So from 0 to omega 1, including omega 1, it will be a compact space. And the theorem says that omega 1 is not delta. And hence, a compact scattered space, which is a segment of all ordinals from 0 to omega 1, including omega 1, is not a delta space. And the proof is quite easy. You take omega 1. It's known that you can divide omega 1 into countable by many pieces, and each piece will be a so-called stationary subset. If you're familiar, I don't know, stationary subset is a set which meets every closed and unbound set in omega 1. This is a classical object in set theory. And then, why you cannot have the property which is defined by this delta property, because by pressing down lemma, we can show that once you have bigger open sets, then the intersection of all open sets, which are expansion of stationary sets, the intersection will be non-empty. And this is a contradiction with our characterization about delta spaces. This is a sketch of the proof why the segment of ordinals is not delta. Okay, now we have some a bit stronger results. We have results that say that X is delta if and only if X is not stationary in omega 1. And also we have a result with Kachuk, which says that X with order topology, it is delta if and only if X has nice topological properties like hereditary paracompact space. Okay, now the question, what we can say more about the properties of compact delta spaces. Here I have to define you several topological notions. I know that it's not so easy to read during the talk. Okay, the most important maybe is the first one. We say the topological space X has countable tightness if the following property holds. Whenever you have a point X which belongs to the closure of any subset A, then you can find a countable subset B of A such that X belongs to the closure of this countable set B. In this case, we say that the topological space X has countable tightness. Another one, what does it mean that X is sequential? It's stronger property. X is called sequential if each sequentially closed set actually is closed. And also, maybe I should tell you what does it mean, the fourth item, what is this pseudo-compact, okay? Everybody in this classroom knows that Weierstrass theorem said that if you have a continuous function which is defined on a compact space, then it is bounded, yes? But in general topology, we consider also a converse. Assume that your topological space X has such a property that every continuous function defined as X is bounded. Okay? In general, it's not the same. It's not equivalent to compactness. In such a case, X is called pseudo-compact. For example, if you take again the space of countable ordinals from 0 to omega 1, then it is pseudo-compact, but not compact. Okay, so we have several statements. Every omega bounded delta space is compact, and the next one, which is also, let me say, interesting and important result, which says that every compact delta space has countable tightness. Okay, so from one point it is scattered, and another characteristic property is that it has countable tightness. And now we can ask if we can generalize this result for pseudo-compact spaces. So the question, is it true that any pseudo-compact delta space has countable tightness? And this is an open problem. From one hand, we have that a theorem which assumes some extra set theoretical tools. Okay, there is some special axiom which is called proper Folkestone axiom. Assuming this extra axiom, we can show that every countably compact delta space is compact, every countably compact delta space has countable tightness, etc. But these results are obtained assuming some extra axiom, and we don't know if this result holds in ZFC alone. This is my first open problem. We don't know. And as I told you, we don't know also for pseudo-compact spaces. So the question is, assume that your space X is pseudo-compact delta. Is it true that X is scattered? We don't know. But if you assume in advance that your pseudo-compact delta space has countable tightness, then we have a result. Then pseudo-compact delta of countable tightness is scattered. This is our result. It's true. But pseudo-compact delta space does not have to have countable tightness. We have an example. So pseudo-compact delta scattered, but with uncountable tightness. So the problem 2 is a hard problem. I don't know how to do it. Now, I put a slide where I'm going to explain you another classical constructions of compact space known and investigated very intensively during last 30 years at least in general topology. It is so-called Mrówka-Izbel compact space. Okay, let me read what I put on this slide. First of all, we say that sets are almost disjoint if their intersection is empty. Oh, this is my mistake. My first mistake. Instead of empty, I should put finite. Okay. Instead of empty, finite. Sorry. The joint is intersection is empty, but if the intersection is finite, then it's almost disjoint. Now, assume that you take any infinite set D, and then you have a family script A of almost disjoint subsets. Then, in this situation, you can define a special topology on a special set. What is a set? The set is the union. Okay, you have first level D, and the second level you add all those sets from your family A. Okay, you consider the elements of the family script A as a points in a new topological space. So the points from D will be isolated, and the base of neighborhoods of this point A, again, A is a point in a new space, but A itself is a countable set. So the collection of all sets of the forms that you take point A itself plus subset B, such that A minus B is finite, then you declare this as an open set in new topological space. And then you have a scattered zero-dimensional Hausdorff space. Okay. If you add extra assumption, here I put any almost disjoint family, but you can do it in a maximal way. Assume that your family A is a maximal one. Okay. So now on this slide you see, assume that D is a set of natural numbers, and this script A family is a maximal almost disjoint family. Usually, such an object we call it MAD family, and then the obtaining space is called Isbell-Mruvka space. And usually in the literature, it's not our inventions. We put the letter psi. Psi of A is a notation for Isbell-Mruvka space. And we have a theorem which says that if you take 1-point compactification of any Isbell-Mruvka space, then this is an example of a compact delta space, which is not Eberlein. So we have two classes of compact delta spaces. One nice class are scattered Eberlein compact, and another class are Isbell-Mruvka compact spaces, which intersects only by countable compact space. Okay, now let me go further, and now I want to consider a MAD family, but which is built with the help of the set of omega 1. So D in Isbell-Mruvka it was just natural number. Now let D be omega 1, and A again will be a maximal almost disjoint family of countable subsets of omega 1. And then we can construct again this space Psi. Believe me or not, but in this case, we don't know, this is an open problem, if this space Psi can be a delta space, for some MAD family in some modulo ZFC, we don't know. But we managed to construct a particular example of a maximal almost disjoint family on omega 1, such that this Psi space is not a delta. So this is an example of a scattered compact space such that the so-called Cantor-Bennigsen rank of scatteredness is just equal to 2, but X is not delta. Okay, sketch, maybe I keep it. So this is a problem 3, okay? I told you that we don't know. The problem 3 asks, does there exist in the FC a MAD family of countable subsets of D with cardinality of D at least alpha 1, such that Psi is not delta? And very Lowest problem, problem 4 asks, are all compact delta spaces countable unions of scattered aberrant compacta? All examples which we have, they actually are countable unions of scattered aberrant compacta, and we do not have any other examples. So this is an open problem. And at the end, yeah, we have Isbell-Nurka space such that if you add only 1 point from the Stonechek compactification, then you lost countable tightness. It's possible. Well, now I ask a very natural question about invariance of this class delta under the natural topological operations. What are the natural topological operations? Subspaces, continuous images, quotient images, products, unions, etc. And here we have several results. Okay, first of all, this is very easy, that the class delta is closed under subspaces. Okay, if you have X any delta space, that any subspace also is delta, this is easy result. Now to the opposite direction, if you have a subspace, Y is a subset of X, and assumes that Y is delta, and the remainder X minus Y is just finite. Then, if you add finitely many points, X is again delta space. If you add only finitely many points. And the next question you ask, what happens if X minus 1 is countable, if you add some countable many points? Here situation is different. What is situation? From one hand, you know that you can destroy delta property. If you add countably many points, then you can lose delta. But we have a result which says that if you add subset which is countable and scattered, then X remains to be delta. So again, assume that Y is a subspace of delta, and it is delta, and assume that the difference X minus Y is countable and scattered. Then X also must be delta. Now, what about the continuous images? Okay, we observe that you can have a situation that you have very good space, like Nurka-Isbell's pseudo-compact space, and you have a continuous mapping from this C onto the segment 0,1. The segment 0,1 is not delta. So on the general continuous images, we lose delta property. Okay, this is proposition 6.5, but if we assume some extra assumptions about this mapping, if we assume that in this situation, phi is a mapping from X to Y, assume that X is delta, but your continuous mapping phi is closed, even more general than closed. We assume only that the image of any F sigma set is closed. Sorry, the image of closed set is F sigma, then we are able to show that the image Y is also delta space. And this theorem 6.6 has many interesting consequences. The consequences are that if you take any countable union of closed subsets such that each subset is delta, then this countable union also is delta. And the next result also is interesting. It says that if you take a sigma compact delta and take any continuous image of this space, then the image also has to be delta. In particular, a continuous image of compact delta space is again compact delta space. Now, what about the products? The story about products is more difficult, but what do we know? We know that the product of two compact delta spaces in some cases, we know to show if it is delta again, but in general, the problem is open. Okay, problem 5 asks, assume that you have two compact delta spaces and then you take a product of just of two of them. We don't know if the product of two compact delta space is again delta space, but you have partial results for some special products, and here this is the statement that if you have got a product of two spaces, but assume that one piece is a delta space without any assumption, and another is so-called strongly sigma discrete space, then we have shown that in the product of such two spaces, we have delta property. Okay, this is particular result, positive result. Good. Now I have maybe the last topic is about the relationships between delta spaces and CP of X. Okay. Here the main notion is the notion of so-called L dominance. What is L dominance? The definition is the following. We say that a space Y is L dominated by a space X if you have a linear continuous operator from CPX onto CPY. Okay, so operator from CPX onto CPY. Then Y is L dominated by X. And there are many topological properties which are invariant under defined relation, and there are properties which are not invariant. And the main goal of this section is to study how behaves the property of being delta space under relation of the L dominance, and also some other properties which are related to being delta spaces. Good. And the theorem here says that if Y is L dominated by X and X is delta space, then Y also is delta space. This is not so trivial result, and it is how to say, it is a result which contrasts very sharply to the property of the class of distinguished locally convex space in general. Why? Because we have very easy examples. You can take Banach space T on the segment 0, 1, which is of course distinguished, and then identity mapping maps it onto CP of 0, 1. Pointwise convergent topology is weaker than norm topology. So in norm topology, it is distinguished. In pointwise topology, it's not distinguished. So in general, the property of being distinguished is not invariant under L dominance. But for CPX, it is, yes, it is an invariant under L domination. The proof, very short proof, goes like the following. You take an operator, your T is an operator, and somehow we manage to lift this operator to T bar, to T hat, let's say T hat, which will be an operator from R to X onto R to Y, from the product onto the product. There is a special lemma which says that this extension is possible, and then the proof goes smoothly. You take any function in target space, you take its pre-image, T hat of G is equal to F, then you can approximate G in CPX by bounded set. Our assumption is that CPX is distinguished, and then the image of this bounded set will be the bounded set in the target space, and it will approximate your function f. This is the idea of the proof. And the same idea also you can apply to the property of Q spaces, okay? Assume that you have two normal spaces, Nx and Y, and assume that Y is L dominated by X. It turns out that if X is Q, then Y also is Q. The same idea, but in this case, you can approximate any function, not just by bounded sets, but by convergent sequences. And this corollary is the bottom line, that if you take two Q sets, for example, assume that X and Y are Q sets, assume that X is Q set, and you assume that Y is L dominated by X. It turns out that Y also must be a Q set, actually, which is a surprising. Well, we have several results, additional results, which says that if you have a pair of metrizable spaces and assume that Y is L dominated by X, then once you know that X is scattered, then Y also is scattered. Okay, so this is actually a new result, and we have some more results in this direction. For example, if you have a pair of space Y and X, and assume that Y is L dominated by X. If X is an Eberlein compact, then Y also must be an Eberlein compact. And if you assume in advance that it's not just an Eberlein, but scattered an Eberlein, then Y also must be scattered Eberlein compact. These results are new. We published them. Referee did not complain. So I was surprised that this result I knew actually. Okay, now a remark that these results are true only if your operator is linear. If you assume that you have a non-linear continuous operator between two function spaces, then you do not have such a result, because there is an example. You can have a surjection, continuous surjective, but not linear mapping from CP, which is onto convergent sequence, onto CP on 0, 1, okay? CP of S. S is just countable convergent sequence. And here you have CP on segment 0, 1. It turns out that we can map CP on the sequence onto CP on 0, 1. Of course, this mapping is not linear. S is countable compact, is scattered. 0, 1 is not scattered. Well, what are further problems? Actually, I saved a little your time, and I'm close to the end. So we have more and more open questions. I just put you some questions which might be more interesting to the audience, because this is a question about Banach spaces, actually. So the problem is the following. Everything we did till now was about pointwise convergent topology. But there are some other topologies. There is a topology which you're familiar with, which is compact open topology. So assume that now we consider the function space is Ck of x and Cky. K means C of x and C of y equipped with a compact open topology. And assume again that you have a continuous linear surjection from Ck of x onto Ck of y, and assume that x is delta. Does it imply that y also is delta? We don't know. This is an open problem. And even in the case of scattered compact spaces x and y, we don't know. So if you assume in advance that x and y are compact spaces, then Ck just a Banach space. So my last problem 7 asks, assume that you have a continuous linear surjection from the Banach space C of x onto the Banach space C of y, and assume that x is delta. We don't know if in this situation y must be also delta. Y must be scattered, that we know. But about delta, we don't know. Okay, thank you for your attention. I finished my.
Questions, comments? Only one comment, because it is quite recent, our discovery. In Prague, I learned there was some paper published by some guy, Andrei Kurka. He considered using some different stuff and different reason working in aspirin Banach spaces. You remember this interval, closed interval, 0, omega 1 is not a delta space. So that means there exists a decreasing sequence of subsets of 0, omega 1 for which we cannot find a larger sequence of open sets still with empty intersections. This is for 0, omega 1. But it turns out that for this segment 0, omega 1, if you take any decreasing sequence of countable sets with empty intersections, then always you can find as larger sets, open sets, containing this our previous stuff, still with empty intersections. So this is essential difference. If we assume only that our sequence, the decreasing sequence, is consisting of countable sets, the situation is totally different. Yeah. So it's not clear why, what is the reason, but must be some reason. So therefore might be some consequence related with the question how to involve aspirant Banach spaces to get this characterization of delta sets in terms of Banach spaces CX. This is quite surprising, the result of this young mathematician. Okay. So no questions, no comments? So thank you again for this lecture. Thank you.
So what about the conjecture for the last problem? So
the last problem, Jerzy says the answer is negative. I think that the answer is positive. Depends whom you ask.
No, the positive answer would be really much more interesting, because you see, the Lindenstrauss many years ago, he told me already the answer here about my question when we had this meeting dedicated to Professor Orlik. And he claimed that he doesn't believe there is one unified characterization of isomorphic character description of Banach spaces here. We have some characterization related with Newton theorem for uncountable intrinsible compact spaces, but for countable we have Besaga-Pełczyński characterization. So at least if the answer is positive, so we can have compact space, which is a delta space. Y is another compact space, and suppose if there is such a conjecture is true, what is written here, that if we have a continuous linear map from this Banach space Cx onto Cy, and if X is delta, then Y must be delta, then we have to control many situations. If you select concrete Y, which is not delta, we know at least for this Banach spaces there is even no continuous linear projection from Cx onto Cy. This is quite strong property. Yeah? So if you look at some papers of Koschmider, he always tries to get some information when Cx could be mapped by a continuous linear operator on another Banach space Cy. It is still open question. So could be some hint or some particular case to have such distinguished examples showing that this map does not exist for concrete spaces X and Y.
But this is a good question. You
But it
invited
might be
also
really difficult.
to try. Question.
But maybe the trick is that in some cases, in some strange compacts, there are surjection for a nice balanced spaces like Hilbert, and then from this if you
No, it might happen, yes.
lifting, then but probably there is a counterexample.
You see, this
I'm not expert, but this is my feeling.
the funny thing here is the following. We have these two Banach spaces, Cx and Cy. And X is delta space, and we are just looking for Y, which is not delta space. So from our characterization, we know already that such a map we are just looking for, or such examples of X and Y, cannot be adapted for spaces CPX, because if CPX is mapped on CPY by continuous linear operator, and X is delta, then Y is delta. Mm-hmm. So such a work should be very delicate to get negative situation related with CP space. It's very interesting, but what he said, he does believe, and I'm a little bit skeptical. No questions, no comments more. Thank you so much.